Greetings to everyone. Today we will be presenting our project titled A Hybrid Centralized Decentralized Multi-Agent Warehouse Navigation System. This project focuses on solving the problem of efficient and safe navigation of multiple warehouse robots operating simultaneously in a shared environment. Our approach combines centralized coordination with decentralized intelligent navigation to improve scalability, safety, and adaptability in dynamic warehouse scenarios. This presentation is structured as follows. We will begin with the problem statement and our proposed solution, followed by the objectives and assumptions made during development. Then, we will discuss the tech stack, agent design, and methodology using the PEACE framework and algorithms used. Finally, we will demonstrate the workflow of the system, AI concepts applied, working demonstration, our learnings, and references. Modern warehouses used by companies like Amazon and Flipkart rely heavily on autonomous robots for transportation, picking, and logistics operations. However, when many robots operate simultaneously, traditional single-agent pathfinding algorithms, such as a star face scalability issues. Fully centralized systems become computationally expensive as the number of robots increases, while fully decentralized systems may lead to collisions, congestion, and deadlocks. Therefore, the challenge is to design a navigation system that ensures collision avoidance, traffic management, and deadlock prevention, while still remaining scalable and efficient. To address these challenges, we propose a hybrid hierarchical navigation system. Our solution combines centralized global planning with decentralized local control. The centralized planner computes optimal global paths and resolves conflicts such as congestion or deadlocks. At the same time, each robot uses a decentralized reinforcement learning-based controller for local navigation and obstacle avoidance. The entire system is simulated using ROS2 and Gazebo, allowing realistic robot behavior and environment interaction. This hybrid approach ensures both global coordination and local adaptability in dynamic warehouse environments. The main objective of this project is to design a hybrid multi-agent pathfinding system for warehouse robots. Our system enables robots to navigate safely in shared environments, avoid collisions and deadlocks, and operate efficiently in dynamic conditions. We combine centralized conflict resolution for safety with decentralized planning for scalability. Additionally, we aim to reduce traffic congestion, waiting time, and total path length. Finally, we demonstrate the real-world relevance of the system using a warehouse simulation. To simplify the problem and focus on navigation intelligence, we made several assumptions. First, we assume a structured warehouse environment with fixed aisles, shelves, and a known layout. Second, we assume reliable robot localization using sensors such as LiDAR and odometry. Third, we assume stable communication between robots and the centralized planner, ensuring continuous coordination and data exchange. Our project is primarily simulation-oriented and does not currently involve physical hardware implementation. Instead, we use Turtlebot models inside a virtual Gazebo environment integrated with ROS2. However, if extended to real-world deployment, the system can be implemented using Turtlebot 3-burger robots equipped with LiDAR and odometry sensors. The project uses the following technology stack. Python is used as the core programming language for implementing path planning, waypoint generation, and navigation logic. For robotics middleware and realistic simulation, we use ROS2 and Gazebo. A star algorithm is used for global path planning, while grid-based cost maps simplify navigation by converting the environment into a 2D occupancy grid. We also use NumPy and mathematical libraries for efficient calculations and coordinate transformations. In our system, each robot acts as an intelligent agent. The agent receives assigned goals or waypoints from the centralized planner, along with sensor inputs such as LiDAR and odometry data. Based on this information, the robot generates navigation actions and physically moves toward the target location. The agent is modeled as a model-based rational agent because it continuously observes the environment, updates its internal state, and selects actions that maximize safe and efficient navigation. This slide represents the peace framework of our system. The performance measure focuses on minimizing collisions, minimizing deadlocks, reducing completion time, and improving path efficiency. The environment is a simulated warehouse with grid-based navigation and dynamic obstacles. The sensors include LiDAR input, local sensing, and global map information. Finally, the actuators correspond to robot movement commands such as wheel, motion, stopping, and turning. Our system combines multiple algorithms and AI techniques. First, a star is used for initial shortest path planning on the warehouse grid. Next, conflict-based search or CBS is used centrally for conflict resolution during congestion or deadlock situations. Reinforcement learning using PPO is applied for local navigation and adaptive decision making, especially in situations involving congestion and dynamic obstacles. Finally, LiDAR based perception provides real-time environmental feedback for obstacle detection and navigation safety. This slide explains the complete workflow of the system. First, the warehouse world defined in the SDF file is converted into a grid-based cost map using the cost map generator. Then, the planner module applies the A-star algorithm to compute the shortest path between the start and goal positions. The generated grid path is converted into real-world waypoints. Finally, the waypoint follower module sends velocity commands to the robot using rows topics such as /cmd_vel, enabling robot movement inside the simulation environment. This project integrates concepts from multiple AI modules. From Module 2, we applied problem formulation, environment analysis, and peace framework design. From Module 3, we used the A-star search algorithm for path planning. From Module 5, we incorporated reinforcement learning concepts for adaptive local navigation and decision making. His slide contains the working demonstration of our project. The video showcases multi-robot navigation, waypoint following, obstacle avoidance, and centralized conflict handling inside the simulated warehouse environment.